let's look at the inverse Laplace transform. The inverse Laplace transform is denoted by the script L to the power of -1. That's the inverse Laplace. It's a notation. And so it is a function of time. So we're still using the ft for function time and capital Fs for the transform. So the inverse Laplace transform of Fs is ft. That's what the first equation says. The definition of the inverse Laplace transform, so this definition is this complex integral because S is a complex variable, right? It has real part, imaginary part, and this is the formal definition. But very rarely we use this as the way of doing the inverse Laplace transform. But this is the foundation of doing the proofs, and also this will guarantee that the uniqueness property. So uniqueness property is that if the Laplace transform of ft is equal to Fs, then the inverse Laplace transform of Fs would be almost equal to ft ut. So almost equal. There are some trivial cases if the ft has discontinuity somewhere. So it could be let's see, if the ut is the Laplace transform of ut is 1 over s, right? So the inverse Laplace transform of 1 over s could be equal to ut, or if the ut defined at t equal to 0, some of the step function defined as what the text did, as that u0 is equal to 1, right? Some define that point as half, as 0.5, and so this trivial case, technically they are not the same, but from any practical purposes, this would be the subtle difference will not make much significant difference in the interim applications. So that's the unique property. So here instead of using equal, so this one here means almost equal. Okay, so but for our purposes, we do this always get a unique solution. Okay, so this trivial kind of non-uniqueness, we are not considering that as non-unique. Okay, so let's look at two cases today. So we're gonna look at the first case with the simple poles. The Fs has a simple pole. Of course, Fs is going to be a rational function, and then we're going to look at the Fs if Fs has complex poles. And we're going to have two video clips to cover the two topics. Let's go to the first one here. So let's see if I have the Fs is a proper function and with simple poles. Okay. So in this case, let's see, this is the proper function. That means m is less than n. Okay, and in this case, we can always break this into. So this means Fs is proper, and it has simple poles means the p1 not equal to p2. I mean, there are no identical poles. So that's what this means. Okay, so they all have simple real poles, and also p1, p2, pn, they are all real. They're not complex numbers. So in this case, we can break down into this smaller rational functions. We call the partial fractions, right? So this is what we call the partial fractions, and it's k1, k2, k sub n are called residues. And so in this case, the reason we call it the residue, we will see probably see in a moment very quickly. And the way we do the partial fraction expansion is to use the so-called cover-up method to find K1, K2, K sub n. We use the cover-up methods. And of course, if you alternate, you could use, let's see, to get a common, you can get a polynomial of the numerator, and using the instead of using the coefficient, you can use the coefficient of this K1, K2, and then you solve the simultaneous equations and you find those. Possibly that's also doable, but that's a lot more complicated than using the cover-up method. We'll see how the cover-up method works. So let's see, if you try to find the K1, what we do is we multiply Fs by S minus P1. By the way, we know the P1, P2, these are the poles, right? So S minus the corresponding pole for this one, and if you calculate this, and this so K1 minus SP1 be cancelled, right? So you will have SP1 time multiplied to the others, and what do you do if you evaluate this, the whole thing at S equal P1, and you evaluate on the right hand side also S equal to P1, what will happen? So in this case, S equal to P1, this is going to be equal 0, going to be equal 0. So all the other terms will be 0, except the first term. That's what we call the residue, right? So add that pole, and basically add that pole there, and you got this residue, right? So, and in this case, what we have is the K1, K sub 1 is just equal S minus P1 times Fs, and we evaluate this here by S equal P1. Okay, and we're gonna look at an example how this really works, right? Looks like amazing, and we can do the similar thing for K2 and K2, and we're gonna multiply that S minus P2 times Fs. And we evaluate that, in that case, we evaluate as second pole there. And then you can do this for all the residues you have. And that's how you, and S minus the P sub n and Fs, and you evaluate that S at P sub n, right? So let's look at this example here. And in this case, let's see, once we do the partial fraction expansion, and then the inverse Laplace transform would be easy, right? So the inverse Laplace transform in this case would be, remember, if each of this term, let's see, the inverse Laplace transform of Kn over S minus Pn, what would this be? Remember, if you do the Laplace transform of e to negative alpha t times ut, the Laplace transform of this one here is 1 over s plus alpha, right? So in this case, if we have if you have e2 minus alpha, if you have e2 plus alpha, and then you're gonna have a negative alpha here, right? Or you can think of this negative Pn as alpha, so therefore the inverse Laplace transform should be ft. This ft here should be e2 minus alpha. Alpha is negative Pn, so therefore you get a Pnt times ut. Right? So that's how you do the inverse Laplace transform once you get this partial fraction expansion. So let's do the first one here and the example, and let's see. We have partial fraction, we have this function here, and this has two poles, right? The first pole is -1, the second pole is -5. Remember S minus P, so all the roots of the polynomial, the denominator. So we have a -1 and -5. But in any case, we can see S minus K over S plus 1 plus k over s plus 2. So this is the partial fraction expansion we're going to get, but the question is how we find these residues, right? So the residues k1, based on what we just discussed, that should be equal s plus 1, which is s minus p1, and times fs, and we evaluate it at the first pole, which is a -1, and in this case what we get, and if we multiply this fs, the fs is this, multiply s to s plus 1 will be cancelled, so we have s plus 2. Maybe I should write this and then so that I don't confuse you. And s plus 2, and I have s plus 1 and s plus 5, and we cancel this one, and now we evaluate this at s equal minus 1, so I have minus 1 plus 2 divided by minus 1 plus 4. Right, I got a 0.5 for key 1. And for key 2, we do the similar thing. Key 2 is s plus 2 times fs, and then we multiply, we evaluate this at s equal -2, -5. I'm sorry, I made a typo here, and this should be -5. Okay. And I should evaluate it at -5, and in this case I have negative s plus 5 times, again here I'm copying the fs, s plus 1 times s plus 5, and s plus 5 we cancel, and then we evaluate at s equal -5. Right, so in this case what we have? We evaluate that at -5. What we have? We have -5 plus 3 plus 2, and we have -5 plus 1, right? I have 3. Okay, I just found an error there on the previous one. As I do this, the result, it kind of raised my suspicion because we have the sum of the residues. But in this one, I think I made a mistake here. This one should be 5, right? And so 1 over 4, that should be 0.25, not a 0.5. So 0.25, and in this case, I have 3 over 4. I have -3. So I have a -3 over -4, right? So I have a 0.75. And the reason is I find this error because I know K1 plus K2 should be equal to 1. We will see the sum residues in the next lecture. And I found that the error, the sum of residue didn't really add up. So anyway, now we can do the inverse Laplace transform. So ft minus ft is going to be inverse Laplace transform fs, and in this case that be inverse Laplace transform of the first one here is 0.5 over s plus 1, right? The second one here is 0.75 over s plus 5, and the first term, as we just said before, so this should be 5 times e2 minus, by the way, the here the alpha is 1, right? So this should be -1 times t. So I just write -t times ut, right? The second one here is 0.75 plus times e2 minus 5t, e2 minus 5t times ut. So if you want to factor that out, that's fine. So that's 0.5 e2 minus t plus 0.7 times e2 minus 5t times ut. Okay, that's how we do the inverse Laplace transform by break that to the partial fraction expansion so that we can recognize the transform pairs. And to take a quick look at the what do we do if we have the how to use the Python or the Google Colab to solve this one. So I have the Google Colab here. I'm going to use the SymPy. This is symbolic module that deal with the symbolic operations. There's a function. So first it set the symbols S and T, and then write the fs. I use the capital F for the fs, and then I do the partial fraction expansion. Let's see. I do. There's a part function. You can do the partial fraction expansion, and of course for the Python, you don't have to have the partial fraction expansion to do the Laplace, to do the inverse Laplace transform. I just want to show the partial fraction expansion. I just run the code. So here the partial fraction expansion is 3/4, which is 0.7, divided by s plus 5, and 1/4, which is 0.5, right? 0.25, we just calculated. And the inverse Laplace transform is going to be, so this would be e2 minus 5t. So this factor of e2 minus 5t. So e to the minus 5t times the e2 4t. So you get a e2 minus t. So that's one term, and you get the 3 terms. So this is the actual result we have. This heavy side t. This is the ut we have. Okay. So that's for the inverse Laplace transform. How you do if you only have proper rational function with unique real poles. Okay, what we call the simple poles.